We've grown up watching amazing science fiction movies like E.T., Close Encounters of the Third Kind, A Space Odyssey, Interstellar, and even our very own Koi Mil Gaya and PK that intrigue us with the idea of other habitable exoplanets, their inhabitants, and the likelihood of all of us crossing paths someday. I mean, who wouldn't want to meet Jadoo, right? Or stretch our legs in the coldest depths of space. But if we were to sprinkle a hint of logic on these outlandish movies, the odds of either scenarios happening are quite slim. While researchers suggesting the possibility of habitable exoplanets have ushered a paradigm shift in cosmology, things are far more complicated than going. That's why a team of AI experts and the astronomers at BITS Pilani, Goa and the Indian Institute of Astrophysics have devised a novel AI-based algorithm to identify potentially habitable planets with a high probability. Professor Snehanshu of BITS Pilani, Goa joins us today to explain how they achieved this amazing feat using the novel anomaly detection method dubbed the multi-stage memetic algorithm.
Trained as a modeler, as a computational modeler. But that's when I joined a private university in Bangalore in 2011, when I was coming back from the US, I was placed in the computer science department. So my bachelor's and master's are in computer and computational sciences, but my PhD is in applied mathematics. So there were some years when I was not doing serious computer science stuff. But then when I was placed there, I had to teach courses in computer science, right? And then in 2013, I first took a very classic textbook on pattern recognition. At that time, that terminology machine learning was not very popular. At least in India, not many people have heard of it. So people were doing pattern recognition, image processing, things like that. Those were more familiar terms. So I picked up that book, I taught out of that book, and that's how it kindled my interest. Very interestingly, that book was co-authored by statisticians and electrical engineers, right? And if you see the early breakthrough in pattern recognition machine learning, most of those breakthroughs are done by electrical engineers and statisticians. Anyway, that's besides the point. And then I started dabbing into the theoretical aspects of machine learning. So I wanted, because of my training, I thought that I could probably focus more on how methods are developed for efficient inferencing, how algorithms are designed, and the complexity of those algorithms, both over small data and big data. So a couple of years passed, and I was still doing just theoretical machine learning. And then I met Margarita in 2015, I think, if I recall correctly. And of course, there was another senior professor at IIA, Professor Jayant Murthy. So I met them, and then we had a couple of discussions. And then Margarita pitched this idea of why don't you come work with us, and maybe your computational expertise might help us. And that's when the first problem that we tackled was actually modeling habitability of exoplanets. Very different from the current work that we are discussing. And there we had designed some computational models. And then it struck me that based on the data that we already have, thanks to a humongous effort of an exoplanet lab at University of Puerto Rico, SRBIBO, that is led by Abel Mendez, right? They are the ones who have created the first database of exoplanets. Right. And then from there, their work is primarily based on the astronomy part. So examining different physical parameters, right? And they have a catalog. In that catalog, they have an optimistic list of exoplanets. Like, what I mean by optimistic list is that they think that some of these planets are potentially more habitable than the ones which are also discovered. So that was a starting point. But initially, when we were doing this, it was primarily exclusively based on the data set that they had created and the levels of the data set that they have created. So if you look at the data set, it has 3 levels of 3 classes. One is non-habitable, which actually dominates the database. And there are 2 other classes, which are mesoplanet and cycloplanet. These are the ones which are potentially habitable. I mean, based on certain physical characteristics, whether they are within the habitable zone of the host star, whether you can have surface temperatures, measured surface temperatures of those planets, so on and so forth. Okay. And so we started developing those methods. And to be honest with you, the early work received some criticism. And these criticisms were valid primarily for the reason that our inferences were based primarily on a very few parameters of those planets, namely the temperature, the flux, and other things, right? And people who work on the modeling side, and that's what we started. In fact, even before we proposed our habitability model, there is a scoring mechanism by the team of researchers led by Abel Mendez, which was known as ESI, Earth Similarity Index. What it means is that since Earth is the only known habitable planet, because we all live in it, right? Okay, its habitability score should be high, and when you try to come up with a quantitative model, you should determine the same score for all other planets. So that was their model. So we improved upon that model, and then we started doing this classification. But all that while, till 2018, till the end of 2018, I did not realize that the problem is better handled if we do not use the labels that are already in the database. Okay, because those labels are actually created based on surface temperature only. Right. And since you cannot measure surface temperatures of many planets, that's not a very good idea. Right. So your inferences will be biased. So that's where we started thinking about this direction, but not right away. Let me be honest with you. What happened was simultaneously, because since my primary, by that time I was, invested heavily in machine learning research. I had another PhD student who is a co-author of this paper, Jyotirmoy Sarkar, whose PhD topic was based on detecting faults and anomalies in large-scale industrial systems. Now, This is a completely different topic from the current theme of the paper, right? But while doing that particular work, and we had some industrial data, real-time industrial data, and unfortunately, because of the IPR thing, I cannot mention the source, but the industrial data was not labeled. So it was not labeled. And so these kind of inferences in the language of machine learning is known as unsupervised learning. Because you infer not based on training your data points with labels, but you infer based on certain similarities between instances that exist in certain classes, right? So Jyotirmoy, I asked Jyotirmoy to develop a method based on an evolutionary algorithm that I wrote a couple of years back, but never used it anywhere. So all these components slowly came together. And then the idea struck upon us that, see, since Earth is the only habitable planet, and according to the astrophysicists, there are only a very few planets which could be potentially habitable from a large pool of discovered exoplanets, which means that the concept of habitability can be made equivalent to anomalies, detecting anomalies. So that's how the hypothesis came about, right? It was in the middle of 2019. But then my other collaborator, Professor Shantanu Sarkar, who is now a senior scientist at ABB Corporate Research, he was not convinced. So it took some time to convince him. And then we redesigned the algorithm and we proposed the hypothesis that, look, if we are able to detect anomalies in that existing habitable database, then that means that we will be able to detect potentially habitable exoplanets. And that turned out to be true. According to the method that we developed, there are a few exoplanets that turned out to be potentially habitable. And that is a subset of the optimistic set of exoplanets that was proposed by other physicists. So it's not entirely the same set. The kind of set that was discovered by us is not, it's like there is no one-to-one mapping between our set of potentially habitable exoplanets and the set that already exists, but it is definitely a subset. So that's the story. That's the whole story of how this came about. I mean, without getting into the technical details. The technical approach is this, that since we are trying to detect instances which are out of the box. So see, most instances are normal instances, right? And there are only a few instances which behave in a way very dissimilar to rest of the peers, right? So there must be some statistical, how should I say, flags that will separate these few points from the rest of the other data points. So what we did was we first went to evolutionary algorithms, like how chromosomes mutate, right? So there exists a well-known algorithm known as memetic algorithm, which means like how genes are memed. Okay, so how you make copies of genes, and from a parent population, how you create child populations and so on and so forth. And the children from different sets of parents then mingle with each other. So something like a cross-cultural idea. So this particular algorithm was then extended on a tree structure. So I don't know if you're familiar with binary trees, but let's say there is a tree that I could draw, and each node of the tree has two subnodes, and these are called children. And then each one of these nodes gets split and so on and so forth, right? So our idea was that we defined an impurity score, and based on that, we traversed the trees, all the trees of each entire database, and found leaves. Now, leaf is something which is where you can no longer be able to split a particular node into two children, right? So it will just be an isolated child hovering somewhere. Okay, and based on the multi-stage memetic algorithm that we designed, we were able to find that all of these isolated children that were somewhere in the tree structure are actually really, really different in terms of their statistical properties from the rest of the population. Okay, and these are the ones which are the anomalous candidates. Okay, and then we took all of these candidates and did a clustering algorithm. And clustering algorithm is an example of an unsupervised algorithm where you do not use the labels of the data points. So it doesn't really matter that there already exists a database where certain data instances are tagged as particular class, certain other instances are tagged as some other class. So we completely removed the labels. And then we also removed the critical points, the points of criticism, that we removed the surface temperature and all other features related to surface temperature so that the inferences are not biased. So ultimately what happened is that three clusters emerged. Okay, one cluster is absolutely normal instances. The other cluster is also absolutely normal instances. And then there are some points lying here and there, not within the cluster. And these turn out to be the anomalies. And since we have object IDs for each of the data points, it was very easy for us to map like which particular exoplanet this particular data point refers to. So in summary, that's the technical aspect. Of course, there are other things like we measured the complexity of the algorithm, the convergence of the algorithm, right? And the other things as well. I mean, the time complexity or whether it is faster than other methods depends on the latent clustering algorithm that you use. If you use a clustering algorithm that already exists, like there are some standard clustering algorithms like k-means and k-medoids, then the complexity of your algorithm will be partially dependent on the complexity of the latent clustering algorithm. But here also, we developed our own clustering algorithm and we empirically verified not only on this particular dataset, but a bunch of other industrial system datasets as well, that in general, what we see is that this particular method converges faster than the existing methods of anomaly detection. And I should mention that there are a bunch of deep learning based anomaly detection methods that exist as well. In fact, there are plenty of such. The number of methods have become so huge that it becomes difficult for any researcher to compare one method with all the existing methods. So what we do is we pick the state of the art. So we compared our method with the existing state of the art, and we showed that the convergence and the accuracy of prediction are either matching or outperforming the existing state of the art. That's how the paper got through. Otherwise, it will not get through a journal like MNRAS, Okay, so the results are like, see, it's a pipeline. And since I'm a very big proponent of open source, we already have a GitHub repository where all the data and the code is there for anyone to use. And this is important for reproducibility as well, right? One of the immediate impact of this paper, what I can see, and this is still a little far-fetched, it's because I don't know if you've heard of Professor Friedman, who is a Nobel laureate in economics, right? In 2006 or 2005, I don't exactly recall when, he wrote a small piece on habitable exoplanets from an entirely economic perspective. The foresight of the gentleman is something amazing, because around that time, at least I am not aware whether the research around finding habitable planets or whether certain planets can be habitable like Mars or not were not so popular. NASA was actually beginning its explorations and they were in the middle of it, right? But he thought of something. I mean, his thought was entirely based on Mars. Okay, so he did not propose any model. He actually just wrote a piece. And then last year, I have another collaborator who is not part of this paper. He's an economist and a professor at Center for Studies in Social Sciences in Calcutta, right? I mean, a trained economics, and he's an econometrician. I mean, he does quantitative economics a lot. We developed a migration model. So where we conjectured that whether if certain tasks of a small select population can be outsourced on a small piece of land in a planet that is potentially habitable, then certain things can be accelerated. Okay, and we designed a migration model because, when you are sending someone to another planet, there is a cost of transportation and other things, right? So against those cost of transportations, which are the hedges, we determined that the return on investment is marginally higher, okay, for really high skill jobs. So I could see that as an immediate impact where certain migration models can be developed and deployed. And you know that people are buying land on Mars. You know that, right? I mean, there are certain people, certain celebrities, they are buying land on Mars. That include a lot of people from India as well. Okay, all right. So whether that model is realizable or not, time will tell from an economic perspective. But if you are asking about the commercial ramification of this research, then that is one thing that I would say, pans out. In any area of science research, right? I mean, we are probably a few paces behind the US and the Western Europe, right? But I would say in terms of using AI in astronomy, there are quite a few people in India who have been actively working on this for some time. Like a few names come to my mind, like for, Professor Ajit Kembhabi at IUCA, Inter-University Center for Astronomy and Astrophysics. In fact, that's one institute in Pune where a lot of people, including the current director, are heavily invested in applying AI-based inferences on astronomical data, right? I mean, particularly image processing like galaxy images. You must be familiar with that discovery 1.5 years back by Katie Bowman, who was at MIT, who first was able to give an impression of how a black hole would look like, right? That's pure AI. That's a really powerful AI. So yes, certain things at this point of time, I would say that the commercial realization might not be that great, but then there are people like billionaires who are investing heavily in this research along with NASA. In terms of the effort from the Indian space agencies like ISRO, right? I am not sure how invested they are, but I think it's a matter of time. It's just a matter of time because I am not the only one. I mean, I must gratefully acknowledge all my peers who have shown directions in this particular area many years before me, right? And so it's a process, you know that, right? I mean, and so there are several people in Indian Institute of Astrophysics and Indian Institute of Science as well who are also doing research in the similar area. And you know that India is part of the Square Kilometer Array mission, and it's a huge, huge project. And there is tremendous scope of artificial intelligence and machine learning with that. And a lot of Indian institutions, including BITS Pilani, are part of this.
Right.
Even in BITS Pilani, there are a few people, both in Pilani campus and Goa campus, who do work in applying artificial intelligence in astronomical inferences. So overall, if you want to know a summary of the general picture that emerges, I would say I'm pretty optimistic. This was going on for last 5 years, if I'm honest, 6 years, right? And several papers came out of which I would say this turns out to be the most influential, not because it got the press, but because of the approach,
right?
I mean, because of the solution approach, right? So I think there are people in IIA, including my collaborator, Dr. Safanova, who has been collaborating with me for several years, I mean, who will take this forward to other areas in habitability as well. I mean, in fact, IIA is the prominent institute in Bangalore. I mean, I think they are doing, if you compare with IISc, there are more people in IIA who are actually interested and have the expertise to take it forward. Right? So I have other collaborations with IIA as well. So where we are looking at other problems in general, right? But yeah, I mean, the physicists, it's very difficult to fool them because, you know, AI can also lead to false positives.
Right.
But when it comes to physicists, they know what is a false positive. Mm-hmm. So you cannot just show them the raw results and, you know, earn their trust. So there are other ways to verify your AI-based results. And that's my biggest learning experience by working with the IIA people, mm-hmm. that there has to be a post-facto verification from a physics side.
Right.
And that is the important stellar contribution of people from IIA, I would say.
The world of cosmology is evolving at a rapid pace, and AI is only going to push the momentum beyond our imagination. In other words, this is another great step for mankind, isn't it? Stay tuned for more insights and updates from the world of data science, analytics, and machine learning at Analytics India magazine.